circular motion is a really important type of two-dimensional motion, and it actually is more like one-dimensional motion, as we're about to see. So if you think about motion along a circle, okay, here's as perfect of a circle as I can draw, and let's just say it has a radius r, big R there. Okay, the object moving in the circle, it could be a ball on the end of a string that you're twirling around. It could be a car on a circular racetrack. It could be something on the surface of the Earth as the Earth spins around. It could even be the Earth spinning around the Sun in a nearly circular orbit. Okay, but the idea is the fact that it's on a circle means it's constrained. If you remember from our inclined problems, okay, we have an incline, and let's say a ball rolls down an incline. It was technically two-dimensional motion because it was moving both down and over, but we were able to reduce it to a single dimension, recognizing that the incline constrained it to move along a line. Well, this circle is a line. It's just a curvy line, and that object can't leave this line. And so we can establish a coordinate system that's curving with the circle, but establishes a zero and the path. And so we often call this the S coordinate. It doesn't really matter, but we often call it an S coordinate. And we say that the object is moving along this circle. Okay? And, well, how do we treat it? Well, we do have our kinematic equations that can be applied to this one-dimensional system. We'd have S final equals S initial plus V initial S times our time period plus our 1/2 AS delta T squared, as well as the other two kinematic equations. So we could talk about this in the same way. So if I say I start here at 0, and let's say I start at rest, but there's an acceleration along the curve. Maybe it's a little rocket engine that's making me speed up around this. I'm holding it on a string or something like that. And the rocket engine is spinning around, and I can get that acceleration. But if I have these, I could solve for a final position, or I could find a final speed or something like that at some time. So I can use these just as I would a one-dimensional problem. I just need to know what that acceleration is along that arch, or along that curve. Okay, now there's another way of describing circular motion. Instead of the arc length, how far along the arc am I, is how many degrees or radians, what angle did I go through. Okay, so I can instead say I went from 0 to 1 meter along the circumference. I could say I went from 0 degrees to 90 degrees, or pi/2 radians. So how are they related? Okay, an important relationship is if you have any arc, okay, with a curve, an arc length along the end, and that arc, or that curve, that S arc length, is related to the angular separation of those two lines by a theta, then S is equal to r theta. Okay, so if this is the radius of that. And just to see, where did this come from? Well, what is the arc length of a full circle? Well, that's 2 pi times r. Okay, that's the arc length of a full circle. Circumference of a circle is 2 pi r. Okay, well, what is the angular? What is the angle of a full circle? That's 2 pi radians. So we have I. Our r just comes down, and we have 2 pi radians are the angular. It's the angular arc length for a full circle, and indeed those are equivalent. They're the same thing. That's actually how we get arc length. So the arc length of half a circle is pi r. The angular distance of a half circle is pi, and so on and so forth. So any arc length is given by any angle times its radius. So that's where they come from. So what's cool about this is we can go in and plug up here, well, s equals r theta. Well, if r is a constant, then I can also say that Vs, which is the derivative of s with respect to time, so that's ds dt, well, that's just r d theta dt. And this d theta dt, we actually give it a name. We call that omega. This looks like a W, but it's a little more curly than a W. It's the Greek letter omega. And that's called the angular speed. Okay? The angular and we can see that it's related to velocity by the radius. So angular speed is the tangential or arc velocity divided by the radius. In a similar way, do this one more time, we could show that the angular acceleration, or sorry, the arc length acceleration, the acceleration along the arc is equal to r times an angular acceleration. Okay, so that is angular acceleration. Sorry, I'm getting squished there at the end. Okay, this is the Greek letter alpha. It looks like a fish. It's the Greek letter alpha. And so with these, we can replace s with r theta. We can replace v with r omega, and replace a with r alpha. And we end up with r theta final equals r theta initial plus r omega delta t, sorry, this would be initial, plus, I'm going to run out of room there, 1/2 r alpha delta t squared. I find r in each of these terms so they can cancel. I'm left with a similar kinematic equation, but now in terms of theta, angular speed and angular acceleration. So I have theta final equals theta initial plus omega initial delta t plus 1/2 alpha delta t squared. So these don't have subscripts of theta on them because they are inherently associated with the angle. Omega is the angular speed, alpha is the angular acceleration. So this is now a kinematic equation for angular motion. This is a kinematic equation for motion along a circumference. And they both are valuable, just like our other ones of x, y, or z, for interpreting this angular motion, this motion along a circle.